By the way, it is pretty hot outside, so it might start getting hot in here really fast. So I might have to turn on the fan later. Hopefully I won't. We'll see what happens. But anyways, until that happens, let's talk about permutation groups. So we've mentioned these before, and if you've done anything in group theory, typically you've seen this because this is something that typically comes up very early on. And if you're doing like a first course in abstract algebra, it might be the first thing you talk, or one of the first examples that you'll talk about. But anyways, so in our cycle, sigma, I'm not going to define what a permutation is because we've talked about it and I assume you've seen it before. You can look it up. But anyways, with that, assuming we know all that, we're just going to jump into R cycles. So this is a permutation such that sigma A1 is A2, and then so sigma AR minus 1 equals sigma AR. Sigma of AR is going to be A1. Wait. Ooh, why did I put that sigma there? Should be sigma of AR minus 1 is AR. This, and sigma of some other index, say B, is just B if B is not B is not one of the AIs, so B is not equal to A1 through AR. So basically what's happening is sigma sends each AI to the next thing. So sigma is acting on the set of indices. We've got indices that we've got at least R indices, possibly more. That's weird. So there's possibly more of them, but it sends each one to the next one. Then when we get to AR, we send it all the way back around to the beginning to AR to A1. Let's see here. And so, yeah, so if any index is not in here, then sigma doesn't do anything to that. Okay? So sigma acts on the indices, let's say A1 through AN, with one orbit of size R and n minus 1 orbits of size 1. Because what's happening here is that if you choose any of the elements between A1 and AR, then if you apply sigma to it, it's going to take you to the next one of these, and then you're going to keep going until you get to AR, and then you'll go back around, and then after doing this R plus 1 times, you'll get back to where you started, which means that there are R different things that there's R different places that you've been to, different indices that you've been to in this process. So that means that the orbit is size R. And then for every other AI where I is strictly greater than R, sigma doesn't do anything to it. So the orbit just contains that one element, and so the size is 1. Okay, so that's the basics of permutations. Another fact, if pi is an Sn, this is the collection of permutations of the indices 1 through n. And of course pi for projection, and sigma is an R cycle. Sometimes I'm going to put these commas in here, sometimes I'm not. It doesn't really matter. Sometimes the commas make it more helpful, but sometimes they're just a little annoying to write them out all the time. So basically I'll write the commas when they're useful, and I won't write them when they're cumbersome. So if sigma is this, then pi sigma pi inverse is just pi a1 through pi ar. Now this is an example where it looks a lot nicer to have the commas in there to differentiate between these. So basically, if you want to figure out what pi sigma pi inverse is, i.e. if you want to figure out what happens when you conjugate an R cycle by some element in the permutation group, you just apply that permutation to each element. So, proof, let B be some index if B is a j for some j between 1 and R, then what happens when we look at pi sigma pi inverse of pi of beta, or pi of b? Then, okay, so the pi inverse and the pi, those are going to cancel out because permutations are bijections on the indices, and so it automatically cancels out. Oh, well, I mean, that's obvious that this will cancel out. But we get pi of sigma of b. So this is pi of sigma of b. Well, b is aj. So pi of sigma aj. And sigma of aj is going to be pi of a, and this is just a j plus 1 mod r. And so that actually, that tells us exactly this, because if, when we say j plus 1 mod r, it means that you just add 1 to j, but if you get to r, then instead of going to r plus 1, you have to loop back around to a1. And so yeah, so what this tells us is that if we're at, so if we apply pi of sigma of pi inverse to pi of b, i.e. if we apply pi sigma pi inverse to pi of ai, then we go to the pi of the next one. And so that tells us exactly that this is how it works, that this will send any of these to the next one of these. So that confirms that these two permutations agree on what they do to elements of the form pi of aj, where j is between 1 and r. Okay? So, if b is not equal to aj for any j, and of course that's j between 1 and r, then pi sigma pi inverse of pi of b, again we get pi of sigma b, but sigma doesn't, since b is not any of the aj's, sigma doesn't do anything to b. And so this is just pi of b. And so that means that, okay, so b is not going to appear as a1 through ar, so then pi of b is not going to appear in the cycle. And since it doesn't appear in the cycle, it's going to be fixed by this permutation. And this confirms that these two permutations agree on what they do to indices that are outside of the a1 through ar, and so they agree on all indices, and so they're the same permutation. And so that proves that. Okay, so corollary. Disjoint cycles commute. Because then what happens if we have pi of a1 through pi of ar, then of course if you've got two disjoint cycles, sigma and pi here is a cycle, then pi, since they're disjoint, pi is not going to move any of these particular indices, and so this is precisely equal to a1 through ar. And so if this is equal to this, well, A1 through AR here, that's just sigma. And so what this means is that in the case where you have two disjoint cycles, this will read pi sigma pi inverse equals sigma. But if you bring the pi to the other side, then you get pi sigma equals sigma pi. And that means exactly that these cycles commute. And so that's how you get that corollary. And we have a fact. Any sigma in Sn can be written uniquely up to ordering as a product of disjoint cycles. And the reason this is true is that what you could do is you could just start at 1 and then see where sigma sends 1 and see where sigma sends that and where it sends that and so on and so on and so forth, and that will give you a particular cycle. Then you go to the next index that doesn't appear in that first cycle, and you do the same thing. You take, okay, let's start with that index, consider where sigma sends that index, then where sigma sends that index, and then so on and so forth, and they'll give you another cycle. And then you go to the next index that wasn't contained, or that does not appear in any of those first two cycles, and you do the same thing, and you just continue this process, and it will eventually end because sigma is an Sn and n is finite. And so you can, so worst case scenario, you go through every single element and you apply sigma to it and it's itself. And so you can do this process at most like n times. And so in particular, it will stop. And so what you'll do is you'll get, you'll be able to write sigma as a product of disjoint cycles in this way. The reason it's unique up to ordering is that if you take any of these two cycles, you can commute them because these cycles are disjoint by construction and they commute with each other, so you can flip them around. The other thing is that it doesn't matter where you start in a cycle. If you have A1 through AR, then that's going to be the same as if you just have A2 through A2, A3, A4, and then all the way up to AR and then A1. So it doesn't matter where you start in here. The cycles, so long as you place A1 after AR, then the cycle will be the same thing. And so they're all the same. And so there's no way to, there's no way that that the process I described could possibly yield, there's no way that you could possibly find another way of writing a sigma in Sn which is distinct from the way that you would get it in the process I described. The only possible changes that could happen is maybe the cycles themselves are in different orders, or maybe the indices in each cycle might be in different orders. In either case, it's basically the same permutation. Okay, so then, so example, 1, 2, 3, 4, 5, and then 6. Sometimes we won't even write the 6 here because sigma b equals b if b is not in any of those. So here 1, 2, 3, 4, 5, 6. You could write this without the 6, it would be the same thing. Also remember that these are permutations, and when you're looking at cycles and figuring out how these move indices, you move from right to left. So if you want to go figure out where 4 sends 5, you start to the right and you move left and you find the first cycle that contains 4, and then you use that to find where it goes, and then you do that. Okay? So this has cycle type 3, 2, 1. And that's because we've got the 3 here, the 2 here, and the 1 here. And we write them in descending order just because, let's see here, it's unique up to ordering, so we just choose a convention and we stick with that. So a corollary of this fact is that we have your conjugacy classes in Sn are in one-to-one correspondence with partitions of n, and this you can write this as lambda 1 greater than or equal to all the way up to lambda L, which is strictly greater than 0, where the sum of the lambda i's is equal to n. So here, for example, 1, 2, 3, 4, 5, 6. So we're using all 6. The reason we include the 6 here is because we're considering this as a permutation in S6. And so we want to write out all 6 indices here. And this has cycle type 3, 2, 1, 3 plus 2 plus 1. Let's see here, we have 3 is greater than or equal to 2, which is greater than or equal to 1, which is strictly greater than 0. And 3 plus 2 plus 1 equals 6. And so this is the correspondence here. This is the conjugacy. This is a representative of a conjugacy class, and this is the partition. And the reason this works is because you can see, let's see here, conjugating a cycle, an R cycle, by anything will give you an R cycle. And so by induction, it's easy to see, or not by induction, but if you have like, yeah, it is by induction. If you have pi sigma 1, sigma 2 pi inverse, then this is pi sigma 1, pi inverse, pi sigma 2 pi inverse. And so the cycle types, and we know the cycle type for pi sigma 1 pi inverse is the same as the cycle type for sigma 1, and that for here is the same as sigma 2. And so the cycle type for this conjugation of sigma 1, sigma 2 is going to be the same as conjugacy for sigma 1 and for sigma 2. So what I mean by that is that the cycle, if you have 2 cycles here, then conjugating by pi is going to give you 2 cycles of the same length. And so let's see here, so then you induct from here, you could put like n sigmas on the inside here, and it would still hold because you just multiply by pi inverse pi in between each pair of sigma i's. And what you get is that the conjugation preserves the cycle type, the disjoint cycle type. Again, that all was assuming that, yeah, that will work if they're disjoint cycle types. And so what happens is that the conjugacy classes in, so I'll say this as a corollary. No, that explains it right here. The conjugacy classes in Sn are precisely the partitions of n. If you take any element in Sn, its conjugacy class is going to be all things. Let's see here. Although I guess you do have to be a little bit careful because it is possible. If you consider conjugation acting on, a R cycle, you want to prove that you can that this is a transitive action, and that turns out to be the case because let's say you have some other R cycle, then you can define pi by where you want what you can choose what this R cycle looks like by choosing pi. Precisely, like say you're at A1 through AR and you want to conjugate it by something to get a new permutation B1 through BR. Then you just say what you conjugate by is you conjugate by pi such that pi sends AI to BI. And so therefore that proves that this actually is transitive, i.e. if you have an R cycle, then then you can find a permutation to conjugate it by to get any other R cycle. And then you induct by that, and you can see that if you've got a permutation with some conjugacy, with some disjoint cycle type, you can conjugate this by some permutation to get any other permutation of this same disjoint cycle type, i.e. so for this one, if there's any other, take any other permutation in S6 of the form which has cycle type 3, 2, 1, you can find some permutation in that S6 which you conjugate this by that permutation and you get that other one. And so what that confirms is that indeed we have this correspondence between conjugacy classes in Sn and partitions of n. And so, yeah, that's an introduction to our discussions of permutation groups, and we are going to go from there.